This video is about the determination of plume rise for calculation of pollutant concentration using Gaussian plume equation. Here I also discuss about the atmospheric stability classes for this purpose. You can see my earlier video number 124 to know more about atmospheric stability. But here we will see the Gaussian plume equation first. In my last two videos, I showed you how to determine wind speed, that is UH, that is wind speed at effective stack height, and how to determine horizontal dispersion coefficient sigma y and vertical dispersion coefficient sigma z. Now to calculate this capital H, that is effective stack height, del H, that is plume rise estimation, is must. Other than the estimation of plume rise, we cannot estimate also these the UH, that is wind speed at effective stack height. Now we just recap here the determination of wind speed at effective stack height. We use this formula where ZA is the anemometer height, that is generally kept is 10 meter. UA is the wind speed as recorded by the anemometer. P is the wind profile exponent, and the value of it depends on atmospheric stability class and terrain. The table shows the value of P for different stability classes for rough terrain. For smooth terrain, the value of P is to be multiplied with 0.6. But for estimating this capital H, del H, that is plume rise determination, is required. And once del H is estimated, UH will be calculated. So other than the estimation of plume rise or del H, we cannot identify H. If you cannot identify the value of H, we cannot get the wind speed at effective stack height. Now, to estimate horizontal dispersion coefficient sigma y, we use this formula, and for vertical dispersion coefficient we use this formula, where x is the downwind distance from the source, must be expressed in kilometer, and a, c, d and f are constants and they depend on atmospheric stability. So the value of A here is only used for the determination of horizontal dispersion coefficient. But you can see that the two sets of value for C, D and F. And when the X is up to 1 kilometer, then these sets of value will be used for determination of C, D and F. And when X is greater than 1 kilometer, then these sets of value will be used. You can see my last video where I solved couple of problems in this regard. Now we already know that Gaussian plume equation requires the input of effective stack height, that is plume central line height above the ground. So, and this requires the physical actual height of the source and then this plume rise. So plume rise is caused by a combination of factors such as buoyancy and momentum of the exhaust gases and the stability of atmosphere itself. Buoyancy results when exhaust gases are hotter than the ambient air, or when the molecular weight of exhaust gas is lower than that of air, or the combination of both factors. And momentum is caused by the mass and velocity of the gases as they leave the stack. And the atmospheric stability is the ability of atmosphere to enhance or to resist atmospheric motion. As the air parcel tends to sink back to its initial level after the lifting acted on it stops, the atmosphere is known to be stable. Whereas if the parcel tries to rise vertically on its own when lifting stops, it is known as unstable conditions. And the neutral condition is when the parcel tends to remain in the same position after lifting stops. So you can, if you need more about this, you will see my earlier video number 1 to 4. Now, this atmospheric stability depends on three factors: thermal turbulence, static stability, and mechanical turbulence. Static stability is related to change in temperature with variation in height, this temperature profile. Mechanical turbulence is due to the function of wind speed and also surface roughness, and thermal turbulence is the vertical air motion generated by convection or convection current. Now, the most commonly method developed by Pascal and Gifford categorize atmospheric stability or turbulence into 6 stability classes from A to F, with A is the most unstable, D is the neutrally stable, and F is the most stable or least turbulent classes. We know this because we have discussed in my last two videos. Now, stability classes are subjective to some degree. The criteria of solar radiation are not sharply defined for all possible conditions and require some interpretation by the user. As the elevation of the incoming solar radiation depends on the position of sun above the horizon, the stability class will depend on the latitude. Here you can see the stability class depend on wind speed and the solar isolation, that is for day, and night is for night cloudiness. So if you can see here the classes of combination, sometimes it is A to B, or C is B to C, or D C to D. And in the case of night cloudiness, when you can see the cloudy when cloud is is more than half of the sky is cloudy, and clear when it is less than is the cloud is less than zero point 0.4 or 0.375. So, and here A is the wind speed measured at 10-meter height. B is clear summer day with sun higher than 60 degree above the horizon. C is summer day with few broken clouds, or clear day with sun 30 to 60 degree, 35 to 60 degree above horizon. And D is the fall afternoon or cloudy summer day with sun 15 to 35 degree above horizon. And E is the cloudiness, the fraction of clouds covered by fraction of sky covered by clouds. And EF takes the average of dispersion of two values, here, and here. And note that regardless of wind speed, always we use class D, that is neutral for overcast condition, day or night. So with this table, we will know that the atmosphere is unstable on you can see that sunny day, neutral or overcast days and night, and stable on clear nights. So for this stable class, you can see it is found in clear nights. Neutral, that is D, you'll find in overcast days and nights. and unstable is for sunny days. And increasing wind speeds leads to more neutral conditions. When wind speed is increasing, we'll reach to this neutral condition. Otherwise, you can see the wind speed is less than 2 meters second, maybe A, B, or E, or even F. So if wind speed is increasing or greater than 6 meter per second, maximum class is under neutral condition. Now, atmospheric stability classes can be determined uh, can be determined based on the vertical temperature difference, that is rate of change in ambient air temperature with height, that is del T per 100 meter. So based on this, based on the vertical temperature difference, this is some stability class. This is found in the nuclear regulatory research, that is a regulatory guide of nuclear regulatory research, US nuclear regulatory mission. In their report or their guide, you will find that when ambient temperature is decreased, is a change of temperature is 1.9 or more, then it is very unstable, and in between minus 1.9 to minus 1.6, then it is moderately stable. And when you can see that the if the ambient temperature changes with height is increasing, then it is stable. And there is another class they have put is extremely stable. When the temperature difference per degree temperature difference in degree centigrade per 100 meters, it is greater than uh, 4. So so you can see the if we want to calculate the plume rise for stable conditions, that is categorized E and F, we use this formula plume rise, and where F is where UH is the wind speed at the height of the stack, which we know by using the formula of getting wind speed of different height. F is the buoyancy flux parameter, which is determined by this formula gr square Vs into 1 minus Ta by Ts, where g is the gravitational acceleration, which is 9.8 meter per second square, r is the radius of the stack, Vs is the stack gas exit velocity meter per second, Ta is the temperature, ambient gas temperature, and Ts is the stack gas temperature. So, and the quantity S is the stability parameter. This is also determined by using this formula. G by Ta is equal to del Ta by del Z plus 0.01 degree per meter, and this G is 9.8, Ta is ambient gas temperature in Kelvin. So this parameter is del Ta by del Z is the actual rate of change of ambient temperature with altitude. So the positive value means temperature increasing is increasing with altitude. So by when you get this Fx and UH, we can identify the del H, and we'll use this formula only when the atmosphere is stable condition. So this category for E and F. So this we have to identify based on our discussion, previous discussion. It is sometimes manual, depends on user. You have to know the wind speed, know the cloud cover, solar isolation. Based on this, you have to identify the category and then use this formula. Otherwise, if the atmospheric stable condition is neutral or unstable, you use this formula. So here is the role of S. You can uh, know, you have to identify the buoyancy flask. So F, and rest is you have to identify this XF. XF is the distance downwind to a point of final plume rise. Now, when the condition is unstable, it is difficult to define the distance downwind at which plume center line stops rising for neutral and unstable condition. It is very difficult when the plume center line stops or the plume rising is stopped. So the following assumption or following is used to determine this fx. So when f, it is depend on f, when buoyancy factor f is 55 m to the power 4 by s to the power 3, the f is greater than or equals to 55, then we use f is, by using this formula, 120 into the value of f and to the power 4, and if it is less than that, then we use this formula. So by using this, we can we can calculate the plume rise for neutral or unstable conditions. So you can read these references to know more. Thank you. Thank you for watching this video.